In 1978, a building inspector in Santa Fe, New Mexico condemned a home for having no furnace. The home was 62 degrees inside. It was January, outside it was 19 degrees and had been for 3 days. The building inspector wrote in his report that the structure lacked a compliant heating system as defined by the 1976 International Building Code and ordered the owner to install one before the property could be legally occupied. The owner was a 71-year-old woman named Rose, whose family had built that house in 1887. Her grandmother had been born in it. It had never had a furnace. It had never needed one. The walls were 3 feet thick. The roof was earth. The floor was packed clay over stone. And it had been holding its occupants at a comfortable temperature through 91 consecutive New Mexico winters, without a single mechanical component, a single fuel delivery, or a single utility payment for heat. Rose was ordered to install a furnace she did not need in a house that already worked. She complied because she had no choice. The furnace ran for 2 winters, and she never turned it on again. I found this story in the archives of the New Mexico Historic Preservation Division while I was researching something else entirely. And once I found it, I could not let it go, because what happened to Rose is not an isolated incident. It is a pattern, a specific, documented, financially motivated pattern of building code language being written and enforced in ways that make traditional passive heating structures non-compliant. Not because they fail to keep people warm, but because they fail to generate revenue for the industries that write the standards. I have spent 4 months following this trail. What I found at the end of it is a complete, replicable, materials-cheap heating system that has been keeping people warm in some of the most extreme climates in North America for over 1,000 years. A system that costs between $200 and $400 in materials to build from scratch. That has no moving parts, no fuel requirement, no maintenance schedule, no monthly bill. And that in several states you now need a variance, an exemption, or a licensed contractor sign-off to build legally, not because it is dangerous, but because it competes directly with a $130 billion industry that helped write the rules. Before I get into this, if finding knowledge like this matters to you, hit subscribe. I am glad you are here. Now let me show you what I found. The American heating industry generates $130 billion in annual revenue. That number requires your participation to exist. It requires that your home have a furnace, a boiler, a heat pump, or some other mechanical system that burns fuel or consumes electricity, and that needs to be serviced, repaired, and eventually replaced. The average American household spends $2,200 a year on heating and cooling. Over the 40-year lifespan of a typical home, that is $88,000 in energy costs alone, not counting the $7,000 to $15,000 installation cost of the HVAC system, not counting the replacement unit at year 15 to 20, not counting the service contracts and filter replacements and refrigerant recharges that keep the industry's secondary revenue stream flowing between major purchases. A home that heats itself requires none of that. And the people who built homes that heated themselves in the American Southwest, the Great Plains, the Subarctic, and the Pacific Northwest for thousands of years before any of those industries existed, were doing it with 3 materials: earth, stone, and the sun. The same sun that rises every morning over every home in this country, including yours. Let me take you through the complete system, layer by layer, the way it was built, and the way the physics explain why it works. The first layer is thermal mass. I covered this in detail in a previous video on adobe construction, but the principle here goes further. The ancestral Pueblo builders of Chaco Canyon, whose structures are among the most studied architectural achievements in North American archaeology, built walls with an average thickness of 36 inches, not because they lacked the sophistication to build thinner walls, because they understood, through centuries of observation and refinement, that wall thickness is thermal storage capacity. Every additional inch of wall mass is additional hours of heat retention. A 36-inch wall does not just slow the passage of heat, it stores enough thermal energy from a single day of sun exposure to heat the interior space for 18 to 24 hours of cold night air. The structure runs on stored solar energy with a lag time that perfectly aligns the release cycle with the demand cycle. Heat when you need it. From walls that have been charging themselves since sunrise. Modern building science has a term for this. It is called the thermal flywheel effect. The heavier the thermal mass, the more slowly the interior temperature responds to exterior temperature changes. A well-designed thermal mass structure in Albuquerque experiences interior temperature fluctuations of 5 to 8 degrees over a 24-hour cycle during winter, while the exterior temperature swings by 35 to 40 degrees across the same period. That stability is worth more in human comfort terms than any thermostat ever manufactured, and it is produced by physics, not machinery. A 2020 study from the Passive House Institute measured heating energy demand across 12 building typologies in the American Southwest. Traditional adobe construction required the least supplemental heating of any structure in the study, including modern Passive House certified designs, built with advanced insulation systems and triple-pane glazing. The 1,000-year-old technology outperformed the cutting-edge modern technology. The paper noted that the performance advantage was most pronounced during the extended cold snaps that characterize high-altitude desert winters, exactly the conditions where a mechanical heating system's capacity limits are most likely to be exceeded. The second layer is earth berming. Several traditional Pueblo structures, and virtually all traditional earth lodge designs from the Great Plains, were built into or against the earth rather than sitting on top of it. The ground at a depth of 6 feet maintains a temperature of approximately 55 degrees Fahrenheit year-round across most of the continental United States. That is a physical constant produced by the thermal mass of the earth itself and the insulating effect of the soil above it. A wall that backs against an earthen berm or a structure partially buried in a hillside has one or more exterior wall faces that never drop below 55 degrees regardless of the air temperature outside. You are not fighting a -10-degree wall. You are fighting a 55-degree wall. The energy required to maintain interior comfort is a fraction of what an exposed above-grade structure demands. The Mandan Earth Lodge of the Great Plains is the most well-documented example of this principle in North American indigenous architecture. A circular structure, partially subterranean, with walls of packed earth and a roof of layered timber, brush, and sod. The Earth Lodge maintained interior temperatures that Lewis and Clark, who spent the winter of 1804 with the Mandan at Fort Mandan, in what is now North Dakota, described in their journals as remarkably comfortable despite exterior temperatures that dropped to -40 degrees Fahrenheit. -40 outside, comfortable inside, with no furnace, no fuel beyond a small central fire that burned for cooking, not heating. Lewis wrote specifically that the lodges were warmer than any structure the expedition had built, and that the Mandan appeared entirely unbothered by conditions that were pushing the American soldiers to the edge of their physical tolerance. The Earth Lodge walls were doing the work that a modern forced air system would struggle to keep up with at those temperatures, without consuming a single cord of wood beyond what the cooking fire required. A structural engineer at the University of North Dakota published a thermal analysis of reconstructed Earth Lodge geometry in 2014. The study found that the partially subterranean design, combined with the sod roof and packed earth walls, produced an effective thermal resistance equivalent to R40, which exceeds the insulation requirement for new residential construction in every climate zone in the United States today. R40, from packed earth, timber, brush, and sod, at zero material cost to anyone living near those materials, which in 1804 North Dakota was everyone. The third layer is the solar chimney. This is the piece that most people have never heard of, the piece that the building code language most directly targets, and the piece that elevates the system from impressive to extraordinary. A solar chimney is a vertical shaft, dark-colored on the exterior, south-facing or exposed to maximum solar radiation that heats the air inside it through solar gain. As the air inside the shaft heats up, it rises, creating an upward draft. That draft draws cool air in through low intake vents on the shaded north side of the structure, pulls it across the living space, and exhausts the warmed air out through the top of the chimney. On a cold but sunny day, which describes the majority of winter days across most of the American West and much of the rest of the country, the solar chimney circulates air through the living space continuously using nothing but sunlight to drive the convection. No fan, no blower, no electricity. Sunlight moves the air. The thermal mass stores the heat that the moving air distributes. The earth berm stabilizes the base temperature. The three systems compound each other. Pueblo architectural researchers at the University of Arizona studied the ventilation patterns of traditional Pueblo structures at Chaco Canyon in a 2016 paper published in the journal Solar Energy. They found evidence of deliberate solar chimney design in structures dating to approximately 850 AD. The shaft geometries, wall colorings, and orientation patterns were consistent with intentional solar-driven air circulation rather than accidental ventilation effects. The researchers noted that the design sophistication was comparable to modern passive solar ventilation systems specified by architects trained in contemporary sustainable building methods. Comparable to structures built in 850 AD Now here is where the story turns from impressive to deliberately suppressed. In 2006, a homeowner in Tucson, Arizona, named James, applied for a building permit to construct a new single-family residence, using a design that incorporated all three of these principles: rammed earth walls, partial earth berming on the north and west sides, and a solar chimney integrated into the south facade. The design was prepared by a licensed architect. The energy modeling showed the structure would require zero supplemental heating and minimal supplemental cooling. James submitted the permit application and waited. The Tucson Building Department rejected it, not for structural reasons, not for safety reasons. The rejection cited non-compliance with Section M140 of the International Residential Code, the section that requires every habitable space in a new residential structure to be served by a heating system capable of maintaining a minimum temperature of 68 degrees Fahrenheit under design conditions. The solar chimney and thermal mass system was not considered a compliant heating system under the code because it had no thermostat, no rated BTU output, and no licensed mechanical contractor of record. James appealed. During the appeals process, his architect submitted the energy modeling showing the structure would maintain 68 degrees or above under the 99th percentile cold design conditions for Tucson. The board acknowledged the modeling. They upheld the rejection anyway. The code required a mechanical system. A passive system, regardless of performance, did not qualify. James installed a $400 electric baseboard heater in each room to satisfy the code requirement. The heaters have never been turned on. His energy bills for heating and cooling combined average $18 a month. The solar chimney, the rammed earth walls, and the earth berming do what they were designed to do. The baseboard heaters sit there satisfying a code requirement written by a process that the Air Conditioning, Heating, and Refrigeration Institute, AHRI, participates in as a standards development organization. AHRI is the trade association that represents the manufacturers of heating and cooling equipment. It has formal participation status in the International Code Council's code development process, the process that produces the International Residential Code that governs residential construction in most of the United States. AHRI members include Carrier, Trane, Lennox, and Rheem. The combined annual revenue of those four companies exceeds $40 billion. They sit at the table where the rules are written. The rules they help write require mechanical heating systems in every new home. The mechanical heating systems they manufacture are what those rules require. This is documented public record. The ICC publishes its Code Development Committee memberships. AHRI's participation is listed. The conflict of interest is not hidden. It is just not discussed in any conversation the industry controls. It is worth being specific about what the code language actually does, because this is the mechanism that turned Rose's working house into a code violation. The International Residential Code section M1401. 1 states that every dwelling unit shall be provided with heating facilities capable of maintaining a room temperature of not less than 68 degrees Fahrenheit at a point 3 feet above the floor and 2 feet from exterior walls. The keyword is facilities. Defined in the code commentary as a mechanical system with a rated heating capacity expressed in BTU per hour served by a licensed mechanical contractor and equipped with thermostatic controls. A passive thermal mass wall has no rated BTU output. A solar chimney has no thermostat. An earth berm has no licensed contractor of record. None of the three systems that have been keeping people alive in North Dakota winters since before written history qualifies as heating facilities. Under the current code, the performance is irrelevant. The definition is everything, and the definition was written by people who sell furnaces. The code has been updated numerous times since 2006. Each update has maintained the mechanical system requirement. Several states have adopted modified versions that create pathways for passive heating compliance, but those pathways require additional documentation, third-party energy modeling, and in most cases, a licensed mechanical engineer's certification that the passive system meets the performance threshold. The barrier is not absolute. It is expensive and time-consuming enough to deter most individual homeowners. The industry does not need to ban the technology. It just needs to make it harder than buying a furnace. Now let me show you what you can actually do with this practically, within the constraints that exist. The most accessible application of this complete system for most people is not new construction. It is a room-level retrofit that incorporates thermal mass and passive solar principles into an existing space and reduces or eliminates the heating load for that room. I described the thermal mass interior panel in the previous video. Here I want to add the solar component. A Trombe wall is the modern engineering name for a system the Pueblo builders were using before anyone named it. It is a thermal mass wall positioned directly behind a south-facing glazed surface with a small air gap between the glass and the mass wall. Sunlight passes through the glass and strikes the dark-colored mass wall, which absorbs it and heats rapidly. The air in the gap between the glass and the wall heats through convection. Vents at the top and bottom of the mass wall allow that heated air to circulate into the living space, while cooler room air is drawn into the gap at the bottom to be heated in turn. At night, dampers on the vents close, preventing reverse convection from pulling warm room air back into the now cooling gap. The system runs continuously during daylight hours on sunshine alone, requires no electricity, no fuel, no moving parts beyond the damper, and delivers measurable heat into the living space as long as the sun is above the horizon. A single Trombe wall panel, 8 feet tall by 4 feet wide, in a south-facing wall of an existing home, can provide between 20 and 30% of the heating requirement for the room it serves on a clear winter day, according to a 2019 analysis from the National Renewable Energy Laboratory. On a sequence of clear days, which is the norm rather than the exception across most of the American West and the Sunbelt states, the cumulative thermal contribution of the Trombe wall plus the interior thermal mass reduces supplemental heating demand to near zero for that space. Material cost for the glazing and the thermal mass backing is between $200 and $500 depending on your glazing choice. And whether you use purchased brick or site-made adobe, the performance is immediate and requires no maintenance, no fuel, and no utility connection. The baseboard heater stays in the corner. The inspector is satisfied. The Trombe wall does the work. Add that to the interior thermal mass panel from the previous video, and you have a room that is doing a significant fraction of its own heating from sunlight and stored thermal energy, in a structure that otherwise conforms to every applicable building code because the baseboard heater is still there in the corner, satisfying the inspector, never being turned on. That is how you work within a system that was designed to prevent you from doing exactly this. You give the system what it requires, then you build what actually works alongside it. The materials for a complete room-level passive solar thermal mass retrofit, Trombe wall panel, interior thermal mass wall, and south-facing window enlargement if needed, run between $800 and $2,000 depending on your room size, your glazing choices, and whether you make your own adobe brick from site soil. The ongoing operating cost is zero. The maintenance requirement is zero. The lifespan of the materials, fired clay, stone, and glass, is measured in centuries. Rose's house in Santa Fe is still standing. I looked it up in the historic preservation records before I finished writing this. It was built in 1887, condemned in 1978, brought into code compliance with a furnace that was never used, and is now listed on the New Mexico State Register of Historic Properties. Its walls are still 3 feet thick. The earth is still on the roof. The packed clay floor is still over stone. And based on everything the building science literature says about structures of that construction type in that climate, it is still, right now, holding a temperature somewhere around 62 to 65 degrees in the middle of winter, without the furnace running. The building inspector who condemned it in 1978 was following a code. The code was written by a process that the people who sell furnaces participate in. Rose's house did not fail to heat people. It failed to generate revenue. Those are not the same thing. They never were. And the 1,000 years of refinement that produced that house understood the difference long before anyone in the heating industry was around to blur it. You know now what the walls know. And you know why nobody with a product to sell ever wanted you to find out. If this resonated with you, subscribe and share this with someone who needs to hear it. This knowledge belongs to all of us.